Yeah. Is it? It's probably sufficiently high definition. Yeah. Okay. So we're recording this. We're recording that. I have to start the timer on the phone. Life is so complicated these days. Okay. So after 25 minutes, it's going to warn me that that camera is going to turn itself off. Have breakfast. Okay, so today we're going to get deeper into excuse me. I may edit that out of the recordings. Okay, so I will scroll down to the bottom of people's comments. So we're going to get into two hard-ish, famous, and not easy problems. So we're going to see, well, actually three, but two of them are sort of the same. We're going to see longest increasing subsequence, edit distance, and building optimal binary search trees. Okay, so it's going to be quite a busy day. If you can follow this, then you should be okay with dynamic programming. Okay? Sort of, except for the stuff I'll teach you next week. Which is dynamic programming but using fancy data structures. So maybe you still have to deal with fancy data structures. And I'm going to start off like I did with Huffman's algorithm. I'm going to start you with what looks like a really easy, stupid problem. Like I was doing with the merging lists. Okay, so consider this problem, which I'm going to call ladders. As in like snakes and ladders, which is you're trying to get from one corner. Now, okay, in snakes and ladders, you're trying to get from the bottom left to the top right. I could have done it like this, but I'm trying to get you from the top left to the bottom right, and you want to cross ladders. Okay, ladders are the red arrows. So at each step, you can move right one cell or down one cell, or diagonally right and down one cell. So you can go from here, you can go to here, you can go to here, or you can go to here. Okay? Now, if you do a diagonal down move and you follow one of these red arrows, then you get a point. Okay? And the question is, how many points can you get? What is the maximum number of points you can get on your way from here, where you have 0 points, to here, where you have however many? Okay? Is this clear? Can you figure it out? Yeah. Like you can get 4. Okay, yeah. But, so if I put this on an exam, people should pass. But we're going to do that if you had a bigger grid, more ladders, then you'd want to do this methodically. You'd want to come up with an algorithm for doing this. So what you would do is figure out what's the max you can get from here by looking at its neighbors. So you would sort of fill in the grid and say, well, if I knew what this value was, I knew what this value was, I knew what this value was, then I could work this out. Okay? So what you could say, if this is, if this is x, y, and z, then well, you have two situations. You have either that. Oh, okay. If you don't have a red arrow, then it is max. I should make you do this. And if you do have a red arrow, then what is it? Last, yes, they only go diagonally in this problem. And I apologize for the rather crappy t-shirt I'm wearing. I was just listening to a PhD defense of somebody who's actually virtually coming here as a postdoc. And so it's in Helsinki. I used to work in Helsinki. I was part of the Helsinki Institute for Information Technology, which is terrible because it's abbreviated HEAT. So you'd say hi, and they'd say, "Oh, you're in heat," and you'd say, "Yes, I'm in heat." Which, if you know what that means in veterinary terms, it's actually embarrassing. But so I wore my old I couldn't find my old University of Helsinki T-shirts, so I'm wearing my old heat T-shirt. People, I have 19. There are 8. And now I have one person just left. I have 17 students. Okay, so randomly selecting. Okay, so it's moving on. My pointer is now on Will Robbins. Are you here? Do you have a microphone? Will Robbins? Does anybody have a microphone? Does anybody know what the formula, if I want to work this out, in the case where I don't have a red arrow, it's max of x, y, and z. And if I do have a red arrow, it's what? Okay. Yes, good. Max of x plus 1, y, z. So, I used to tell my students that the way to think about these problems is, suppose you have this very friendly, slightly weak-willed professor, and so you have the problem and you're like, "Oh, prof, I don't know what the answer is," and the prof will say, "Oh, well, what would it be if this were this and this were this?" And like, "Well, I don't know what that is," and the prof will tell you, but the prof just has barely enough self-discipline to not tell you the whole answer, but they'll tell you the answer to any smaller subproblem. So I had a biology teacher in high school who was like this. And you say, "I don't know the answer to question 2. And you'd say, "Oh, well, it's like this, isn't it? It's like, what would it be?" And you'd be like, "Yeah, I don't know." And you say, "Oh, well, it's 7, isn't it?" And you'd be like, "Yeah, okay, 7. I don't know that answer to question 3 either." So in this case, if the prof told you, like, this is a 3, and this is a 2, and this is what? This is also a 3, and then you say, "Okay, well, this is going to be a 4." Okay, so you can get it. So that's. But then the professor becomes a little bit, after a while, the exam has gone on a bit longer, and the professor has become more obstinate, and so they're not answering questions here, but they'll answer smaller. So you can work this out if you can work out this, this, and this. You can work this out if you can work out this, this, and this. You can work this out if you can work out this, this, and this. So you can always push it back sort of recursively. Now, the thing that makes this different than recursion is your professor is weak-willed, but not quite so weak-willed that they will answer the same question over and over again. right? So remember I said you can answer this if you can answer this, this, and this. You can answer this if you can answer this, this, and this. So this was x, right? So to calculate y, you ask the professor what the answer to x is. But then to calculate this, you also ask the professor what the answer to x is. Well, the professor isn't going to want to tell you the same thing over and over again. So this is sort of recursion, but a bit more efficient in that you don't solve the same subproblem over and over. You keep a table, and when you find out the answer, you write it down. So, okay, what would we actually do? We would say this is, let's fill in this in, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, this is a 0, this is now a 1. This is a 1 because it's the max of these three. This is now a 1. It can be either from here or from here. This is a 1 and this is also a 1, right? Because either to get to here with 1 point, you can either go down this red arrow and then go across, or go down this red arrow and then go across, or go down this red arrow. And then this is 0, 0, 1, and this is 2, and this is 2, and 2, and 2, right? And if I make a mistake, please correct me. And this is 0, 0, and this is 1 either this way or coming from this. And this is 2, and this is 3, and this is 3, and this is 3, two possibilities here. This is still 0, 0, this is 1, this is 2 either from this or from this. This is 3, this is 3, this is 3, 0, 0, 1, 2, 3, 3, and this is 4. Okay? So, you all understand, right? You all think I'm wasting your time, and this is an incredibly easy problem, and like you can't believe this is in third year. Good. Excellent. I will try not to smile evilly when I say that. Okay, so actually, just like when we did that merging list problem, we were actually solving, we were actually designing Huffman's algorithm. We just solved another problem, which is called longest not increasing subsequence, that's next week. Longest common subsequence. Okay, and we just found the longest common subsequence between the strings Canada and banana. Okay? So what are the red arrows? The red arrows are where B doesn't match anything. A matches with this A. And it matches with this A, and it matches with this A. N matches with this N. A matches here, here, and here. N matches with this N. A matches here, here, and here. So I put the red arrows arriving at the cells where I have a character here matches a character here. The ith character, well, this is the empty string in both cases. So that's what that's doing there. That's why there's nothing here. So to remember the dynamic program for finding the longest common subsequence, just think of it as crossing red ladders, okay? Because you can figure that out. Longest common subsequence is a bit trickier, but it's the same problem, okay? Why? Well, let's suppose we have some string, and it's x1, x2, xm, and we have some string y1, y2, but yn, it can be a different length. And we want to look at, so the longest, did I say substring? I mean subsequence. In case I say longest common substring, I mean longest common subsequence. So what is the longest common subsequence of Canada and banana? Well, it's ANAA, right? Because there's an AN, A, and an A, and ANAA. And it's 4. No, substrings have to be continuous, subsequences don't. Okay. Okay. So, why, let's consider why we just solved this problem. Well, suppose we have this x1 to xm, y1 to yn, and what we've done is we want to have m rows and n columns. Yeah, m rows and n columns. So let's suppose we have, oh no, my marker is dying. So let's suppose we're working out yj minus 1, yj. Can you see this? Maybe not. I use black too much. Okay, so let's go to, so we have x1, xi minus 1, xi, y, bleh, y1, yj minus 1, yj. Okay? So this, what is the longest common subsequence of the empty string and the empty string? I only have 18 students. Empty string, what is the longest common subsequence of nothing and nothing? It has length, nothing, yes. What is the longest common subsequence of nothing? So y1 to ym can be Canada, and x1, they happen to have the same length in this case. M and n both happen to be 6. But this could be, you can think of this as banana if you want. So what is the longest common subsequence of the empty string and C? nothing. And the longest common subsequence of the empty string and anything is nothing. There is nothing in the empty sequence. The same thing here. What is the longest common subsequence? So you're going to want to fill this grid out such that cell ij, so this is counting from 0, 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Such that cell ij contains the length of the longest common subsequence of x1 to row and then column xi and yj. So let's suppose that you filled in all the rest of this, and now you want the length of the longest common subsequence of x1 to xi and y1 to yj. Well, how do you get that? So you can think, if I have like kana and ban, so what I can have is let's say bana. If the ith letter in this string, no wait, this is the one along the top. So I want it to be the jth letter here. Okay, so this is bana and hana. If these two letters match, then I have the option of saying, if these two letters match, then I can take the longest common subsequence of these strings, and then I add 1, right? So if these two letters match, then I have a red arrow here, and I have the option of taking this and adding 1. Or I can say, maybe I'm looking at banan, and this, I say, well, I want this character to, the ith character here matches to an earlier character here, so I ignore this character, and I keep this subsequence that, say, is like this. Okay? So if it's the case that the characters match, I can take this and add 1. Or, if they don't match, then I can just take whatever subsequence existed, and I don't choose them. Or I can take the subsequence in this that matches to some earlier part, and I can throw this character away. Or, what I can do is match these two. Yeah, I can have an n, and I can throw this away, right? Okay, so let's actually do this. So which one? We want bana and bana. Let's say we have one banan. Okay, so I is 1, 2, 3, 4, 5. J is 1, 2, 3, 4. So what is, so here is, we're in this case, because these two don't match. So what is, this one is So this is 5, 5, this is 4. So what is 4, 3? What is the longest common subsequence of bana and can? It's 2. Okay, I'm just going to stop the video and start it again.